No, people are kind. All right.
Why don't we have...
Chapter 9, Section 5. Chapter 9, Section 5. Summation notation. You have seen this in Algebra 2. The Greek letter sigma is used for summation. A summation is when we are adding a bunch of values together. So summation notation of some sequence, a sub 1, a sub 2, a sub 3, a sub n. If I want to show that I am adding all these values together, I do my sigma right down here, and the book does it a little better than I do. The summation of a sub k of this expression, where k equals 1 to n. This tells us where we start, so that is our beginning or initial value, and this tells us how far we go, where we end. So you can see right there is how we read that. The sum or summation of a sub k from k equals 1 to n. K called the index of summation. A little story here. Mr. Gauss, when he was in elementary school, he was just a little boy, and he was done with his math too soon, evidently. And his teacher was a little bit perturbed, because then little Mr. Gauss would make a nuisance of himself and bother the other students. And so she said, okay, come here. I've got a little project for you. Take your little slate and your little slate pen, and you take the numbers 1 plus 2 plus 3 plus 4 all the way to 100, and you work on them, and then you come back when you're done. So the teacher was all thrilled and happy because she figured she would have at least 30 minutes of peace and quiet while the little Mr. Gauss was down there working on his summations. Well, about 30 seconds later, he comes back and lays his slate down. Done. She says, no, you can't be done. You didn't do it right. Yes, I am. I'm all done. So she works and checks, and he was right. So how is he going to get that answer so quickly? So you ready? Go. You're remembering a formula. Well, here's what little Mr. Gauss thought of. He says, you know, if I do these numbers 1 plus 2 plus 3 all the way to 100, and then if I reverse them, 100 plus 99 plus 98 plus all the way down to 1, and add these together, what's 100, or 1 plus 100? 101. What's 2 plus 99? What's 3 plus 98? You notice, hey, every time I get 101. Now, how many of these numbers are there? How many of these sums are there? There's 100 of them, right? But he has just doubled what the answer should be, because he did it twice. So if he takes all these, the number of 100s there are 100 101s, but he doubled them, so he needs to divide it by 2. So what's 100 divided by 2? Well, 50. What's 50 times 101? I'll let you use your calculators. But he just uses slate pen and pencil and pad, whatever you call the things. 5,050. See? He said, oh, that's no problem. I know the answer to that. Well, this idea is a series, it is called. When we add up a sequence of numbers, we get a series. And he came up with the idea of the formula. If I take the number of numbers I had 100. And if I divide it by 2. And then multiply it by, now where did we get that 101? Well, this was the first number, and this was the, which number? Last number. The first number and the last number. A sub n. There's a formula right there that we just get for a nice finite. What does finite mean? It ends. We only did the first 100 numbers. It ends. Arithmetic sequence. It's an arithmetic sequence because we were adding 1 each time. 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1, etc. Right here is the formula. Now, I wrote it slightly different. I brought that 2 in front. That happens to be how we learned it in Algebra 1. A sub 1, the first term, plus a sub n. Either formula is the same. Either formula works for you. Make sure you know that formula. The sum of a finite arithmetic sequence. Now, this means I need to know what the first term and the last term are. What if I don't know what that last term is? Oh, well, earlier we learned what any term in an arithmetic sequence is. It's the first term plus n minus 1 times, do you remember how to get any term in an arithmetic sequence? D, the common difference. You'll need to make sure you have that memorized in this chapter as we do this work. So I can find the last term if I don't know the last term. And if you actually distributed that d out, a sub 1 plus n times d minus d, and then I put it, oh, I guess they didn't distribute that d out. If I just put this expression right here, where that thing is, and notice they pulled the 2 out front, n over 2, I'd have a sub 1 plus a sub 1, 2 a sub 1s, plus n minus 1 times d, plus n minus 1 times d. So this is a formula when I don't know that nth term, that last term. You don't have to memorize the second one if you don't want to, as long as you know how to get the nth term, which you are supposed to know. So we can use this formula to sum the terms of an arithmetic sequence right over here. A corner section of a stadium happens to have 8 seats along the front row, and each successive row has 2 more seats than the row preceding it. The top row happens to have 24 seats. So how many seats are in that entire section? So here's the idea. You have 1, 2, 3, all the way to 8 seats, and then it gets bigger as it goes up this corner. And the very last row has 24 up here. How many seats are in that whole section? Well, I know what my first term is. My first number of seats is 8. I know what my nth term is. Happens to have 24. Now I just need to know how many of these rows do we have? Well, we don't know yet, and we're not going to count it out because we want to be able to do it if they say start with 8 and go to 6,234,000. We don't want to count it out. So, well, this is my nth term. I know that my nth term is my first term plus n minus 1 times d. And so I know 24 must equal my first term 8 plus, now I don't know the number of row we're on, but I do know the common difference. What's one row to the next row? 2 in this case. 2 more seats. 2. So let's just solve this for n. Well, 8 plus 2n minus 2 equals my 24. So 8 minus 2 is 6. Subtract 6 from the 24. That gives me 18 is 2n. So what is n? Ah, there are 9 rows. There are 9 rows in this corner section of the stadium. Now I can figure out the sum of this. The sum of those 9 rows is going to be, got that formula memorized?
24 divided by 2.
Number of rows. Now I'm going to do it how this book does it. First term 8 plus last term 24 divided by 2. Let me back up just a second. I am using, where did it go? Oh, I'm on the same page. I am using that formula right there. Number of terms, I have 9 terms, 9 rows. First term plus last term, 8, 24 divided by 2. Thanks, Carlos. So let's see if we can do this math. What's 8 plus 24? 32 divided by 2. 16. 9 times 16. How much? There you go. There are 144 seats in that corner of the stadium. Isn't that nifty? You can do this on your calculator. We just looked at a question where you were wanting. Here is the formula for getting the sequence. We're doing a sequence of, and notice they just wrote the formula right here. We're starting with 8 plus n minus 1 times 2, the common difference. There's our formula. N is our variable. We're starting with the first term and we're going to the ninth term. We had to figure out it was 9. And they put the sum of that sequence. Let's try it. Get your calculators out. See if we can make it work. The sum of that sequence. How can I do it where everybody can see what's going on? I'll figure this out. There we go. Now I've got it all inside the red box. So if I want the sum of that sequence, let's see if it's in the list operations, if the sum is there. I might have to look it up. No, we don't want the cumulative sum. So I'm going to go to the catalog. There's catalog. Catalog is right above the 0. And then I'm just going to hit C. And we'll find it. It's under another menu, but we'd have to go looking. There's a lot of C things.
What if it's C? Would it be S?
You know, S usually starts with, sum usually starts with S, doesn't it? Oh, good thing this is math class and not English class. Let's start with S. That's why I was only finding the cum sum. See, somebody said it. Juwan said it, and that's messed me up. So it's her fault.
What I feel like it
Sum. There it is. I found it. Sum of the sequence. Now that's under our list, second list. Ops, operations. Yeah, it's summation of a sequence. So yours may look a little different. You'll have to play around with yours. Yours probably says that. 8 plus parentheses, and you can use any. I'm going to use alpha n, just because they're using alpha n, minus 1 times 2. So there's our formula, comma, our variable alpha n, variable is n, comma. We're going to start with the first term, comma. We're going to go to the last term. And then we're going to close up our sequence there, and we're going to take the sum of that sequence. Sure enough, it's 144. It takes longer to do that than to do it by hand, finding all those commands. But it works. It can be done on your calculator.
Just you find the sum and then put the sequence?
Mm-hmm. Except I didn't find the sum. I let the calculator do it all for me. So it's the summation of that sequence is what it is. And like I say, if your operating system looks a little bit different, maybe set it aside and we'll figure out how to do it in your operating system if it's not working for you yet. You don't have to do it with the calculator. They're just demonstrating to you that it can be done. Sum of a finite geometric sequence. Now in arithmetic, remember we're adding the same thing each time. What's happening on a geometric sequence? Do you remember? We're multiplying by a common ratio. Couldn't be a fraction, may or may not be a fraction. We're multiplying by a common ratio. So there is a formula, we'll want to memorize it, for the sum of a geometric sequence. And this is finite, it doesn't go on forever, it stops somewhere. So a sub 1, the first term, times 1 minus the common ratio to the n power, the number of terms we have, divided by 1 minus the common ratio. So let's see if we can figure that out. It says find the sum of this geometric sequence. Well, here's our first term, and they were even nice enough to tell us our last term way out there, whatever that thing is. So if I am going to find the sum of all these terms together, so the sum of these terms, I don't know how many terms I have yet, do I? Well, let's just start filling it in, the values I know. I know the first term, 4. I know my nth term, I don't know which term it is, but it's that thing. 4 times negative 1/3 to the 10th power. Now I need to know how many terms are there, because I need to know n, and I need to know what my common ratio is in order to do this. I want to start by finding my common ratio, because I can take any two values. To get my common ratio, wow, we're bouncing around, aren't we? Negative 4/3, divided by 4. Take any term divided by the previous. It'll give us our common ratio. Well, instead of dividing by 4, I'm multiplying by 1/4. That's the same thing. And the 4s would cancel. What do you get?
Negative 1/3.
Negative 1/3. Negative 1/3. There happens to be my ratio. Number of terms. Oh, we're going to do a little bit of a use of knowledge. I was going to say we're going to cheat a little, but we're not cheating. We're using our knowledge. But we have to have some knowledge. What's the nth term look like for a geometric sequence? A sub 1, first term, times common ratio to the n minus 1 power. Make sure you have that memorized. I know we learned that before break. So just like that, arithmetic has an nth term, a sub 1 plus n minus 1 times d. A geometric one has an nth term, a sub 1 times r to the n minus 1 power. Well, look right up there. If that exponent, by the way, a sub 1, do you notice it? 4. 4. Common ratio, negative 1/3. Ooh, negative 1/3. We just figured it out. To the n minus 1 power. Well, if n minus 1 is 10, what does n equal? 11 minus 1 would be 10. There must be 11 terms in this one. And so we can do our cool formula. Now here, there it is on the calculator. Entered it in. But we're going to do it by hand up here using that formula. So a sub 1, 4 times 1 minus r to the n power. 1 minus negative 1/3 to the 11th power. Divided by 1 minus the common ratio. 1 minus negative 1/3. Now, I'm going to simplify the bottom part because it's real easy. 1 plus 1/3, 4/3. Try it out. Get your calculators. And I will let you either do it with this by hand formula, or you can do the sum of the sequence down there if you want to. I'll give you a minute. I know Eng already has it figured it out. Oh, you don't have it already done? Yeah, Eng already has the number figured out, but I'll let the rest of you work a minute here. Where's your calculator?
I just lost it.
Is it? What if you do answer to fraction? Does it give you a nice fraction or not? I don't know if it does or not. I haven't looked at it. That's what mine says. Eng, what did you get? That's what you got? 3 point. We don't like that 2.99 one. Yeah, it probably doesn't do it to fraction. That's the number you should be getting. No, but that's as far as the calculator took it. That's it. 3.000016935.
Is it for sure found some?
Did you? Where is it under?
It's in stat, and it's in the math ops.
Second stat. Oh, it's under math? Oh, look at that. There's some. Whoops, there's some. There you go. Now we have sum and sequence. Don't have to look it up in the catalog. Very good. All right. Infinite series. So what's an infinite series? Never ends. How can I get a sum of an infinite series? Ever thought of that?
N plus blah, blah, blah.
Well, there must be a formula. But can there really be a sum of an infinite series? If something goes on, how can I ever have an answer to adding those things all up? Won't it just keep getting bigger and bigger? Well, it depends. Do you remember when we learned converging and diverging series? A converging series gets closer and closer to a limit, a value. Well, if I get closer and closer to a value, then maybe I can add them all up because I know what I'm getting closer and closer to. If we took, here's the one we just did, right there. 4 was our first term, negative 1/3 was our common ratio, and they're saying, let's leave it with n, and find the limit of this as n goes to infinity. Instead of just saying we're doing the first 11 terms, let's just keep going and going and going. Well, what happens to this fraction when you raise it to a higher and higher power? Negative 1/3 to the n power when n is approaching infinity. When you square it, cube it to the 15th power, what happens to the size of that negative 1/3? It shrinks. It gets smaller and smaller and smaller. It limits to 0. It's getting closer and closer to 0. So there it is. It's limiting to 0. And 4 times 1 minus 0, well, that's just 4. 4 divided by 4/3 is the number. Hey, if we do this one forever, it goes to 3. Notice our answer was 3.0000, whatever it was when it did it 9 times. Well, if we keep adding more and more and more terms, it keeps getting closer and closer and closer to 3 is what happens for it. So we can have an infinite series. We have the summation from n equals 1 to infinity up here. And we can have a sum to that, provided that each term would limit to 0. Now, what we did earlier is called a partial sum, where we had the first 11 terms. That's a partial sum of that infinite series. As long as it converges, as long as those terms converge, then there will be a sum of the infinite series. We can have a sum of this infinite series. It will limit to this number s. Now, if those things diverge, then there is going to be no sum. You can't do it. So if your numbers are getting away from some value, it's not going to happen. That just gets bigger and bigger and bigger. So let's look at these partial sums and figure out, is this one going to be able to actually give us a sum to an infinite series or not? For each of the following series, find the first 5 terms in the sequence of these partial sums, and which ones appear to converge? Which ones are going to be ones that if it was infinite, we could actually get an answer to it? Well, they want us to actually find the first 5 terms. 1, 2, 3, 4. I need to do another term here. 0 point, what's the pattern?
0, 0, 0.
I need 4 zeros then, don't I? 1, 2, 3, 4, and then a 1. So the first 5 terms, which of the series appear to converge? Actually add those together. Now it's easy to do it in your head. 0.1 times 0.01 is 0.11. Times a 0.001 is that. Times a 0.001 is that. I'm just getting this thing right over here. What do you think? Does this appear to converge? Look at the pattern here of these numbers.
Yes.
I'm getting smaller and smaller, aren't I? I'm getting closer and closer to 0. These one appear to converge. This one happens to be 1/9. Take 1 divided by 9. What do you get? 0.1 forever. If I do that as an infinite series, it's 1/9. Now, that partial sum is not 1/9 because it stops. But infinitely, it would just be 1/9. Let's see, 10, 20, 30, 40. Oh, we'd have to add 50. So how about this one? Does this one appear to converge? No. This thing's just getting bigger and bigger and bigger. No. 1, -1, 1, -1. It'd be a 1. How about this one? Does this one appear to converge? No. If I have one of them, my answer is 1. What if I have 2 of them? What's my answer if I add 2 of them? 0. If I have 3 of them, what's my answer? 1. If I have 4 of them, what's my answer? 0. Is this one getting closer and closer to a value? No. So these 2 would not have infinite sums, those last 2. But that first one would have an infinite sum. Sum of an infinite geometric series is going to be true if the absolute value of that common ratio is less than 1. If the thing we're multiplying by each time is less than 1. Let's look back at these for a minute. What was I multiplying this one by each time? 0.1 times what is 0.01? 1 what? Actually, 1/10. 1/10 times 1/10 is 1/100th. 100th times a tenth is 1/1000th. That common ratio is 1/10. That worked out. What are you multiplying part B by each time? Oh, we're not. That one's not. That one's arithmetic, isn't it? We're just adding 10 each time. We have a common difference of 10, so that one's not going to work. How about this one? Are we multiplying by anything to get each succeeding number? -1. 1 times -1 is -1. -1 times -1 is 1. 1 times -1 is -1. That has a common ratio. That is geometric. We're multiplying by -1. But this one does not qualify. This one does for that stipulation that the absolute value of the common ratio must be less than 1. That one equals 1. Absolute value of -1 is 1. So it doesn't work. But this one, 1/10, does work. And as long as it does work, here is the very simple formula for it. It's just your first term divided by 1 minus the common ratio. Determine whether this series converges or not. And if they converge, then we can find the sum. And notice these are all infinite series. We go to infinity. Okay, well, how do I determine if it converges or not? I need to figure out what my common ratio is. I can figure out my common ratio by looking right at that formula. Can you tell me the common ratio? Let me come back. It's 0.75. Let me come back right here. Here we were. Remember our nth term? Where did I write that? Did I write that down somewhere? I thought I wrote it down somewhere. In a geometric sequence. Oh, I did write it. Right here. I wrote it down. Right there is our geometric sequence. First term, common ratio to the n minus 1 power. Well, this is geometric. First term, common ratio, they're just using the variable k. Common ratio is 0.75. Will that converge if it has a common ratio of 0.75? Yes. Check. Absolute value is less than 1. So yes, it will. So we are going to find the sum of this. A sub 1, what's my first term?
1.
Now, there's two ways of getting this. This fits exactly the nth term formula for a geometric series. First term, common ratio, n minus 1 power. Another way, they say k equals 1. That means I start with a 1 in the k position. Well, 1 minus 1 is 0. Anything to the 0 power is 1. 3 times 1 is 3. So my first term is 3. 1 minus common ratio. 1 minus, I'm going to call that 3/4 because it's easier to work with fractions. 3 divided by, what's 1 minus 3/4? 1/4. Instead of dividing by 1/4, I'm going to multiply by the reciprocal. If you do this one forever, it will equal 12. There's the sum of that sequence. So let's try this one right over here. What's the common ratio? It's -4/5. I'm going to be a little careful about getting my first term this time. I'm actually, because notice this is n, not n minus 1 or k minus 1. So I'm actually going to substitute in a 0 there. This one starts at 0. Well, what's anything raised to the 0 power?
1.
1. First term is 1. That's all I need to know. So this one does converge, and its sum will be my first term, 1, divided by 1 minus the common ratio. Now, if I did that in fractions, 1 minus a -4/5, or 1 plus 4/5. 9/5. 5/5 plus 4/5, 9/5. So that's going to equal 1 divided by 9/5. Instead of dividing by 9/5, I'm going to multiply by 5/9. And 5/9 times 1 is 5/9. There's my answer. There's what that sum is. So let's try this one. What's the common ratio? Pi over 2. Does this one converge? What is pi over 2?
Oh, yes, it does. No, it doesn't.
No, it doesn't. Pi is 3.14 divided by 2. It's 1 point something. That's 1 point something. 1.57. I don't really care what it is. It's just bigger than 1. No, I can't get a sum out of that one. How about this one? They didn't give us the formula. They simply gave us the numbers.
Yes.
1/2. We're multiplying by 1/2. So yes is the answer. So if I want to get the sum of this infinite one, I do, what goes on top? What's on top then? 1, the first term. 1 divided by 1 minus 1/2. 1 minus the common ratio. What's 1 minus 1/2? 2. Do this one forever, you get 2. Are we done? No, not quite. Not sure why I have it way down there instead of at the top, so I'll just fix that. We can convert repeating decimals to their fraction form using this idea. Repeating decimals, only repeating decimals, pi is not, but repeating decimals are rational numbers. Rational numbers then can be written as a simple fraction, which is the sum of all these things, right, G1? So if I look at this, I would call my first term the part that is being repeated, 0.234. My common ratio, what do I multiply that by to get my next part? Well, I multiply it by a 0.000. Whoa. Let me change that. I multiplied it by 1,000th to get my next part that I add. If I take 0.234 times 1,000ths, I have moved the decimal 3 places to the left, 234, which if I added these two together would then give me that next part. And then if I multiplied it by 1,000ths again, I have another 3 zeros, which would then give me the next part. So how I find my common ratio is, it's 1 over however many decimal places are being repeated. I have 1,000th that is being repeated, 3 decimal places. So now I can write this, remember, a sub 1 over 1 minus the common ratio. My first term, and I'm going to do it in fractions, that's 234 over what? 1,000. Divided by 1 minus 1 1,000ths. What's 1 minus 1 1,000ths? One minus 1 1,000th is 999 over 1,000. And if I inverted and multiplied, you awake out there still? Instead of doing this, well, those 1,000ths would cancel out, and I'd have 234 over 999. Now, that may reduce to, that may still reduce, and it does, 9, I think. What does it reduce to? Is it 78 over 333? 26 over 111? If you divide them both by 9, is that what you got? Or maybe you just let your calculator do some work for you. Let's see if that works. Take 26 and divide by 111. What do you get? Should get 0.234. It should keep repeating. Now, how will I do a problem that has more than just the repeating part? Look right here. Here is a 0.4 with an 8.5 repeating. Well, I have to pull out that 0.4. That's not repeating. That's not an infinite sum. 0.4 is 4/10. So there I wrote it 4/10. Plus the repeating part. Here's my infinitely repeating. That 85 thousandths. Notice that's in the thousandths place. 85 thousandths. And I am multiplying it by 100th. I have to move it 2 decimal places. So 1 minus 100th. I'm just using the formula, which would be 99 hundredths right down here, which we can invert and multiply right down here, which we can reduce and then take 4/10 plus 85/990, and we get 481 over 990. And then you can check it. Take 481 divided by 990 and see if it gives you 0.48585. This keeps you awake.
Yes. No, yeah, it does.
So you see what we had to do? We had to pull out the non-repeating part on this one. Okay, you guys can work.